Any questions? All right, we last left off talking about simple harmonic motion, or the implications of Hooke's law. Remember that Hooke's law is that the force on something that obeys Hooke's law increases proportional to how far something's been displaced. So if the slinky obeyed Hooke's law, it would take a certain amount of force to stretch it this much. If I stretch it twice as far, it takes twice as much force. And you'll sort of sense that. I mean, slinkies aren't great springs, but it does get stiffer and stiffer the farther I pull it. So let's take a look at the simple case of, we have a 2 meter long ideal spring, and I attached a 4 kilogram mass to it and put that 4 kilogram mass in equilibrium. So first off, what is the spring constant? Well, it's
kx. U equals 1/2.
You're going for the potential energy formula. It'd be x squared, but not yet. We're not dealing with energy. We're looking at forces here. So, hey, let's do a force diagram. Except now we have a spring involved. F tongs. All right, so what are the forces acting on the 4 kilogram mass?
You have weight going down.
Tension going up.
We're talking about a spring, so let's be more specific, because we do have an independent formula for it. Unlike tension, which generally is always problem specific. All right, we have these two forces. What's the, going through the process, direction of acceleration?
Are we doing the one in equilibrium, you said?
Yes.
So, nowhere.
Okay, so now we pick our coordinate system. What do you want to make the positive direction?
Up.
Okay. And decomposition, do we have to break up either of these vectors? I got 2 heads shaking back there. I got 1 in the middle. Do I get a fourth? Do I have a fourth person today? Oh, I've got 4. All right. Feels like a groundswell. All right. Equation of motion. These blues are sad. Let's try this one. What's the equation of motion?
The force minus weight
The force. I'll read your mind on that one.
equals MA. No, actually just equals 0.
It is MA, that is absolutely correct, but it is specifically 0 in this case. Now, we could have saved some time and just said the forces up equal the forces down, but why do it the short way when we can do it the long way? All right, so we have Fs equals mg. Now, the negative sign here is indicating direction, but we already taken that into account because the string is stretched. The minus sign means that the force is up. And so we have K delta X is equal to mg.
No. Didn't we establish that up was positive?
Yes.
So what if the minus mean that as it's being pulled down, it's negative?
Then, so you're saying it should be a negative there, and then I'll have a negative for delta X.
Depends on where we put 0.
And delta X is how far it's stretched from equilibrium. So, yeah, you could establish a 0 someplace else, but let me just sort of recommend with the spring, always set 0 equal to where equilibrium, to where, yeah, I'm potentially going to contradict myself later, but to where equilibrium is. And obviously, we have a spring sitting here by itself, and then we have the mass on it. In this case, it sits 0 there. But if you would like, on your own, you can set 0 anywhere. And just work through the extra complications.
So with each one of these, it's at equilibrium?
No, this is not.
And the middle one?
Yes, that is equilibrium. That is just the spring sitting there.
Oh,
As Jim V12 would say, fat, dumb, and happy. All right, as far as the negative goes, the negative is telling us that that force is upwards. So the magnitude of the force up is equal to the magnitude of the force down, which is characterized mathematically that way. All right. So therefore, K, the spring constant, would be equal to mg divided by how much it's stretched. So 4 times, we'll put it on this planet, divided by what?
Zero. Yes.
Divide by 0?
Well, if it's in equilibrium, and we choose, you just said it's probably a good idea to do displacement or put 0 at where it's at equilibrium. It would be 0.
Yeah, that was the contradiction that I warned you about. Then after that, I said set 0 equal to here for this part.
Okay. So
It's how far that action causes it to stretch. And again, the complications are, I'm going to talk about the complications later on.
well,
Right now, let's just take it this spot right here. Is how far does that cause it to stretch from here?
3
All right,
meters.
meters.
thank you. So this would be 4 kilograms, 9.8 meters per second squared, and 3 meters. All right, you work through the math, and you get
13.0666.
I assume 6 keeps going.
Yeah.
Units?
Kilograms per second.
You actually could almost go that way. You left something off.
Kilograms.
Oh, it's crazy.
Kilograms per second squared is perfectly fine. Traditionally, they just do newtons per meter. But kilograms per second squared is not wrong.
It just sounds a little weird.
Newtons per meter?
No, kilograms per second squared.
Yeah, it does seem odd.
Kind of like a foot-pound.
Foot now.
All right, so now I take this 4 kilogram mass and I pull it down and I let go. Because we're dealing with something obeying Hooke's law here, the spring is going to oscillate in harmonic motion. We can characterize the path it takes by the sine and cosine functions that we talked about last week. But for right now, I just want to know what is the acceleration of that mass. So if I pull it down that additional amount, then, well, I still have the force from the spring minus the weight equals, it's just not 0 anymore. So Fs minus the weight is equal to ma.
So, are we not putting into the equation you pulling it down?
The fact that there's, well, the spring force is going to be different because it's stretched down farther and acceleration is not 0.
Yeah.
So we got the equations of motion, substitution. For what do we have an independent formula?
W
Okay.
mg.
And yeah, we have an independent formula for W. We also have an independent formula for
Acceleration.
it's not traveling in a circle.
K delta X.
Yeah, for the spring force. We're left that blank. All right, so let's plug and chug. It's the same spring, so I know what K is. That's 13.06 repeating times some number, minus, that was 39.2. 39.2 is equal to 4a. What number goes here?
It would be the displacement from wherever we put 0, which if we do it when at equilibrium, it would be 5. I think I'm reading it.
Which equilibrium are we looking at?
I was just going off the one in the middle.
That is a very good question.
Well, in this situation, I think they're all the same spring, like you just said, and we established the middle one with equilibrium, so that one is the one we would use.
All right. Yes, and good question, and no. It depends. So, for right now, we are going to use the 10, not 10, we'll use 8 meters. We'll pick the same zero as we did last time. And then we'll get into how we can make it to 5 meters, but we have to do something else first.
So we just do when the spring is just by itself sitting with nothing happening?
The way we're doing it now, yes.
Okay.
We don't have to, but again, there's something else we have to do first. All right, so that's not 10,
8.
yeah, 8. So we end up with whatever that ends up being. So A equals, and someone's going to tell me the magic number.
$16.32 meters per second squared.
All right. Suppose instead we went with sort of Jack's first thought of the fact that it stretched 5 meters. So if I do 13.06 repeating times 5 meters and say that's equal to 4a, so mass times acceleration, what's A now?
Wouldn't we also have to include the weight?
We're about to find out.
It's the same thing.
What? What a coincidence.
Who would have done?
So notice, just in this one example, that if we ignored the weight as a force, we pick equilibrium to be, or we pick 0 to be here. But if we bring the weight into the equation, we pick 0 here. Now, I'm about to go into the derivation about why that works. Any questions before I start spewing letters onto the board?
So there is the, if you start with that equilibrium, what is that equilibrium called? Just like equilibrium without a force on it?
Yeah, that's basically length of the spring.
So if you start with the length of the spring, you have to incorporate weight.
Yes.
If you start at an equilibrium with weight on it, you can leave weight out of it.
Correct.
Does it work that way because they're both 4 kilogram masses in the spring? Or is that, you just chose 4?
It's still the same spring. It should. Oh, he's making the same mass. If we did change masses, we would have to know where the equilibrium, if this became 8, we would have to know how far does this stretch with 8 on it.
Okay.
Because we need to know how far it stretches from where equilibrium is with the 8 kilogram. All right, other questions? Then let's do some math, which is why we're all here. All right. So looking in the third situation there, I have k, x. I'm just going to drop down to x instead of delta x, minus mg equals ma. Since we're doing letters here, this stretch right here is, we'll call it A, and then it's going to stretch again, an additional B. So I have kx minus mg equals ma, and that's from the third position right there. I know x is how far it stretched from the initial, just the length of the spring, so this would be k a plus b. That's the total length that it was stretched, minus mg equals ma. Let's distribute. So Ka plus Kb minus Mg equals Ma. But in that middle position, that middle equilibrium position, we have the spring force, the magnitude of the spring force is equal to the magnitude of the weight. In that position right there, we had K times how far it stretched is equal to mg. So for that particular mass, Ka equals mg. In other words, that and that cancel out. And all we're left with is just Kb equals ma, which is what I had written up here. It's the spring constant times how far it stretched from the new equilibrium spot, or from the middle position, is equal to ma. And the same thing holds true with dealing with energy. That if I wanted to look at how fast the mass was going at some particular spot, I could use, well, actually, let's do it. We'll do it two different ways, at least, and show that we keep getting the same answer. Questions before I continue erasing?
So for that problem, the KB, we're just taking that B section that we just wrote and plugging it into that equation so we can cancel out the first part. And that's technically the new zero.
Yes. Anything else? All right. So I want to know how fast is this moving when it goes through this spot right here, when it passes its equilibrium position. So first way we're going to do it is with the equations of motion. Sorry, wrong wording. With the trig functions. I know that position for something in simple harmonic motion is equal to some amplitude times cosine or sine. Cosine makes more sense here, times omega t. The velocity is equal to a omega, negative a omega sine omega t. And acceleration, negative a omega squared cosine omega t. Now the reason I'm picking cosine instead of sine is that I'm starting at an extreme. I pull it down to its amplitude and I let go.
So you would recommend just looking at it kind of like a graph and choose the one where it's either in the middle or extreme.
Yeah. Now in reality, if you were doing a lab with this, then yeah, you aren't going to hit it perfectly. So I know that my amplitude is how far I pull it down here, so that would be 5 meters. So and my amplitude is 5 meters, again, that's E. Omega is the square root of K over M. We did get that last week, that's the angular frequency is equal to the square root of the spring constant divided by the mass. So that would be 13.06 repeating over 4 and then square root of that. Someone's about to reveal the answer.
And W here is
That's omega.
omega here is representing
angular frequency. And if they're calling to find that out, they're going to be delighted. So what do we get? One point eight. 1.806. Units?
Newton meters? No. Dividing.
All right, so this would be the square root of a Newton per meter over kilograms.
Newton per meter.
Square root Newton meter over kilograms.
I would take off of that.
I would just take off the
Newton per meter kilogram. The way you said it, you had meters on top.
would you take off the sign and there'd be Newton meters per kilogram?
So take,
Newton.
no, take. All right,
Just
if you're dividing like this,
Mhm.
that would be, because I think that's where Ibrahim's going, that's a Newton per meter kilogram.
Mhm.
Square root. The common easy unit of square root of newtons per meter kilogram. Is that where you were going?
Yeah.
Okay. Although I think you said Newton meter also,
Yes.
which is what he had said. Great minds, think alike.
No,
What is a simplified form?
newtons per meter per kilogram squared.
No. How'd you get that?
Because, well, I just didn't like looking at the square root, so I just put it in and squared it.
Uh-huh. Yeah, that doesn't work that way. Not how math works.
It's not how much.
All right, what is a Newton in its base form?
Kilograms. Is it times meters per second squared?
All right,